Hello everyone and welcome to episode 4 of Explaining Physics Concepts. In this video we're looking at thermal physics and part 1, where we're just going to be looking at what do we mean by internal energy. And okay, let me just make it end. So we have internal energy, and then we're going to take a look at thermometric properties, and then those thermometric properties we're going to be looking at range, sensitivity, and etc. that we have done previously in our smaller classes as well, but we're going to be taking a look at in more detail and depth. Starting off, what do we mean by internal energy? So internal itself just tells you something that is inside the particle, right? So if I were to say internal energy is essentially the sum of energy of particles in random motion. So when you have, let's assume there is a small box, and then there are so many particles inside, and all of these particles are in random motion, and all of these particles, they possess some kind of energy, and that total energy is given as internal energy. Now how do we classify that internal energy? Number one, first is random distribution of kinetic energy. First is random distribution of kinetic energy, and the second is random distribution of potential energy. Random distribution of potential energy. Okay, so when you add up the kinetic energy, and when you add the kinetic energy and the potential energy, both of these energies, they give you the internal energy of a particle. Now we know what kinetic energy is. Kinetic energy is, it refers to the movement of particles, right? So first point, it refers to the movement of particles. So the particles are moving because of the kinetic energy. And this energy, this is a very extremely important point, this energy is only affected by temperature. So only temperature affects it. So when only temperature affects it, we call it as specific heat capacity. If it's confusing, you do not have to worry, because I'll be explaining specific heat capacity in our next video. So we just have to know that when it comes to kinetic energy, as temperature increases, the motion of particles, it also increases, something very basic, and that is just related to specific heat capacity, which I'll explain. Now let's come to potential energy. Now what do we mean by potential energy? Potential energy, it refers to the intermolecular spaces. So this refers to the intermolecular spaces. So when you see particles and you see the spaces between them, this is what you call potential energy. You must have seen gravitational potential energy, chemical potential energy, elastic potential energy. So these are like more specific form, but in this we're only looking at the potential energy, which just refers to the intermolecular spaces. And now intermolecular forces or intermolecular spaces, that is what you call potential energy, and this only happens when there is a change in state. Happens only, so you see how when there is a change in temperature, only then the random distribution of kinetic energy changes, but when there is a change in state, only then the random distribution of potential energy state. And also this word random distribution is quite very important. You cannot just say kinetic energy, you cannot just say potential energy. Happens only when there is a change in state. When there is a change in state, and that is what you call specific latent heat. If I were to sum it up, you'll say, okay, when you see particles, the total energy in them is referred to as internal energy, and then you further classify them, the movement, when these particles move, that is referred to random distribution of kinetic energy, which is only affected by temperature, and the spaces and the intermolecular forces and the spaces that you see between them, that is referred to as random distribution of potential energy, and that is only affected when there's a change in state. So you must have seen how when they're solid, the particles are very close to each other. When they become liquid, they move further away, so there are more intermolecular spaces. So when there's a change in state, there is a change in potential energy. Now let me tell you something very interesting. When you must have heard of PV equals N or T. This is a formula you must have seen in your older classes as well. This is you must have seen it in chemistry as well, but if you don't take chemistry, this is a formula for ideal gas. Now, an ideal gas, and there were many properties, characteristics of ideal gas. Ideal gas, one characteristic that we need to know here, that in ideal gas, the intermolecular forces, let me write it, the intermolecular forces are negligible. The intermolecular forces in ideal gas are negligible. So do you see the word intermolecular forces? When they are negligible, which means the potential energy then becomes negligible, and everything. So in an ideal gas, potential energy does not exist, and it only depends on the random distribution of kinetic energy, right? So we said intermolecular forces are negligible. That means they cease to exist in an ideal gas. So when they don't exist, that means potential energy does not exist, and it only depends upon the random distribution of kinetic energy. So I would say, when you talk about ideal gas, in an ideal gas, its internal energy only depends upon random distribution of kinetic energy. And I hope that made sense. Now we're done with internal energy. We're going to move on to thermometric properties. You must have studied the things that are needed to make a good thermometer. Sensitivity, good range, good response, it should be responsive, etc., etc., right? So we're going to take a look at all that in further detail. Okay, starting off strong, what do we mean by thermal equilibrium? When you start breaking the words down, you will find it very easy to see what they mean. Thermal, heat. Equilibrium, there is an equal level, which means regions of equal temperature. That is what it generally means. And then the next definition is thermometric property. You must have heard this word somewhere in your life. And thermometric property means a property. Let me quickly type it down. A property that changes with temperature. A property that changes with temperature, and that thermometric property, it should have number one, good range, number two, sensitive, it should be sensitive, number three, it should be responsive, and number four, it should have linearity. So this is what it means when we say thermometric property. The thermometric property, and you must have seen these words to make a good thermometer. So thermometric property is something that is inside the thermometer, and all of these things, and it should have good range. It should have good range, sensitive होना चाहिए, responsive, and linearity. Now let's look at these words in more detail. Let's start off with range. Okay. Now, what do we mean by range? Range, the maximum and minimum. You must have heard the word range in mathematics. Maximum divided subtracted by minimum. So the max and minimum temperature to be measured. So if you see in a thermometer, you see 0 degrees and then you go up and you see the maximum temperature as well. Next is, let's look at the word responsive. What do we mean by responsive? How quickly a thermometer registers changes in temperature. How quickly a thermometer registers changes in temperature. So let's see whether it instantly changes from 0 degrees to 1 degrees, and if the thermometer is able to register that change, that means it has good responsive, or it's very responsive. Next, if we look at sensitivity. Sensitivity, the change in thermometric property, the change in thermometric property per unit change in temperature. Per unit change in temperature. So yes, when you first hear the word sensitivity, it sort of like seems similar to responsive, how sensitive it is to the outside, but no, it means responsive is related to thermometer, how quickly it registers changes in temperature, and sensitivity is related to how quickly the thermometric property changes with temperature, right? So if you can see, let's say, let me give you an example. You have a thermometer here, and then you have this, and then it changes this much for like a certain part. So like how much, if there's one Kelvin or degree Celsius change, how much does this thermometric property change with it? It could be this much, or it could also be this much. So for 1 unit change in temperature, for 1 degree or 1 Kelvin change in temperature, how much does this thermometric property change? It could be this small, or it could be this much, right? And then you have linearity. So what do we mean by linearity? For every unit change in temperature, the thermometric property undergoes an equal change. Now, if all of these words seem very confusing, and since they have like similar terms, you just have to know when it comes to responsiveness, how quickly it responds to the outside temperature. When it comes to sensitivity, when there's a 1 degree change in temperature, 1 degree or 1 Kelvin change in temperature, how much does the thermometric property change? Linearity, linear. There's a linear relationship. For every single time there is a unit change in temperature, the thermometric property, so let's say if this is the change in temperature, the thermometric property should undergo an equal change. That means they have a linear relationship. Pretty simple, right? And then these were the definitions. If I were to tell about the properties, so these were the things that should be present in a thermometer, right? So these are the properties of a thermometer. So the properties on which thermometer can be made: density of a liquid, volume of gas at constant pressure, resistance of a metal. So, not, I don't want to confuse you, but these are just the properties on which a thermometer can be made, right? You have a thermometer, you can take the density of a liquid, you can use these properties to make a thermometer. But the main part of all of this was that you need to understand what is internal energy, what are kinds of internal energy, that there's no random distribution of potential energy in ideal cat. Then you talk about what are the properties of a thermometer. It should have a good range. So when you want to know, if someone asks you what is a good thermometer, something that has a good range, something that is responsive, that has good sensitivity, that has linearity, and then you understand what these actually mean. How do you differentiate between them? And that is pretty much it for part 1. In next part you will be looking at specific latent heat to vaporization, and I have a very interesting question, past paper question, that I've seen a lot of students stress about, and I'll be solving that. So stay tuned and have a good day.